26,000 light-years away, at the very heart of our galaxy, something is wrong. A black hole, 4 million times the mass of our star, sits in a space smaller than our solar system. Stars orbit it at speeds that should not be possible. Ancient energy lobes larger than anything we have ever measured erupt silently above and below us, and an unexplained glow of gamma rays pulses from the center with no confirmed source. Tonight, we travel inward, past the gas clouds, the magnetars, the stars circling in opposite directions, past echoes of ancient explosions and objects that defy every rule we know. If you enjoy the journey, like and subscribe. Take a breath. We go in. Look up on a clear night, and you will see the faint smear of the Milky Way stretching across the sky. But the center of that smear, the actual heart of our galaxy, is completely hidden from your eyes. Not because it is too far away, because something is in the way. Between us and the galactic center sits 26,000 light-years of gas, dust, and debris. Thick clouds of material absorb visible light almost entirely. For most of human history, we had no idea what was at the center of our own galaxy. We lived inside it, orbiting it, carried along by its rotation, and we could not see it at all. That invisibility shaped everything. Ancient astronomers who mapped the sky had no idea the galaxy even had a center the way a city has a downtown. The Milky Way looked flat, uniform, and without clear structure. It was only when we built telescopes that could see in radio waves and infrared light wavelengths that pass through dust, the way a radio signal passes through a wall, that the center finally revealed itself. And what it revealed was nothing like what anyone expected. The first signals that came back from the galactic center were strange. Radio telescopes picked up intense, chaotic energy pouring out of a region far smaller than anyone had predicted. The signal was compact, bright, and unlike anything in the surrounding galaxy. Astronomers labeled it Sagittarius A because it sat in the direction of the constellation Sagittarius, and at its core was something even more compact still, something they called Sagittarius A star. But before anyone could understand what that object was, they had to reckon with the environment surrounding it. The galactic center is not peaceful. It is one of the most violent regions in the known universe. Stars are packed together at densities millions of times greater than in our neighborhood of the galaxy. Gas clouds slam into each other at tremendous speeds. Radiation floods the region from every direction. Magnetic fields twist through the space like invisible rivers running in all directions at once. And yet, in the middle of all that violence, there is an object sitting quietly, waiting. And that object is the reason nothing adds up. Picture standing at the edge of a city so dense and chaotic that buildings are constantly collapsing and rebuilding, and at the center of it all is a single locked room that nobody has ever opened. That is approximately the situation astronomers find themselves in when they study the galactic center. Everything around it is extreme, and the thing at the middle is, by some measures, surprisingly calm. We will get to that contradiction. But first, consider what it means that we are talking about the center of our own home. This is not a distant galaxy we are observing from the outside. This is the structure we live inside, and for most of human history, we could not see its most important feature. What finally changed was not just better telescopes. It was a completely new way of thinking about what a galaxy actually is and what sits at its foundation. Because it turns out, every large galaxy we have ever studied has something massive at its center, something that should not, by any logic we understand, be able to exist in the space it occupies. And what comes next is the moment astronomers actually found it. In 1974, two radio astronomers pointed their telescope toward the center of the Milky Way and picked up something they could not explain. It was a point of radio emission so bright, so compact, and so unlike anything else in the galaxy that it immediately stood apart. They named the broader region Sagittarius A. But nested inside it was a source so small and so intense it got its own designation, Sagittarius A star. Nobody knew what it was. The leading theories ranged from a dense cluster of massive stars to something far more unsettling. It would take decades of careful observation to get an answer, and the answer turned out to be stranger than most had dared to suggest. The breakthrough came from tracking stars, not the region in general, individual stars. Starting in the 1990s, 2 independent teams of astronomers, one in Germany and one in the United States, began patiently photographing the same patch of sky near the galactic center year after year. Using infrared cameras that could peer through the dust, they watched as stars near Sagittarius A star began to move. Then they watched more carefully, and more carefully still. What they saw stopped them cold. The stars were not drifting slowly, the way stars normally move across decades of observation. They were racing, looping, curving sharply around an invisible point in space. One star in particular, designated Stu, was moving so fast and tracing such a tight elliptical orbit that the only explanation was a gravitational source of almost incomprehensible mass sitting at the center of that orbit. To bend a star's path that sharply, that quickly, you need an object with roughly 4 million times the mass of our star compressed into a region smaller than the distance from our star to its nearest planet. By any measure we have, that is a black hole, a supermassive black hole sitting at the center of the Milky Way, 26,000 light-years from where you are right now. This was confirmed. This is not a theory. The Nobel Prize in Physics was awarded in 2020 to the scientists who led these observations. And yet, the confirmation raised more questions than it answered. A black hole of that mass should be doing things. It should be pulling in surrounding gas and radiating enormous energy as that gas heats up and spirals inward. Other galaxies with supermassive black holes at their centers blaze across the universe, outshining entire galaxies. We call them quasars. Our own central black hole, by comparison, is almost completely silent. It is sitting in the middle of one of the most chaotic regions in the galaxy, surrounded by fuel it is barely touching. That is one of the core mysteries we will return to. The thing was found. Its mass is confirmed. Its location is pinned. And still, the equations do not balance, because finding the black hole was only the beginning. Once astronomers knew where to look and what they were looking for, they started noticing things in the surrounding region that the textbooks had not predicted. Things that accumulate, layer by layer, into a picture of the galactic center that challenges nearly every model of how galaxies are supposed to work. The next layer is the one that first made researchers genuinely uncomfortable because it involves stars. And stars near a black hole of this size simply should not exist. 4 million times the mass of our star. Sit with that for a moment. Our star already contains more than 99% of all the mass in our entire solar system. Everything, the planets, the moons, the asteroids, the comets, all of it, together, makes up less than 1% of what our star alone contains. Now multiply that star by 4 million. That is the mass we are talking about at the center of the Milky Way. And all of it is packed into a region of space roughly the size of our own solar system. This is where the math starts to feel wrong. When you compress that much mass into that smaller space, the physics we use to describe ordinary matter completely breaks down. No known force in the universe is capable of holding that much material together in that smaller volume without it collapsing into a singularity. A point where our equations stop producing meaningful answers. This is confirmed science. Sagittarius A star is classified as a supermassive black hole because nothing else we know of could produce the gravitational effect we observe. But calling it a black hole is in some ways just a label we attach to our own ignorance. What is actually happening at the central point of that object is unknown. Our best theories of physics, general relativity, and quantum mechanics both fail at that boundary. Think of it this way. Imagine trying to compress the entire Pacific Ocean into a glass of water while the water stays liquid. That is the kind of density ratio we are dealing with, except in this case, the compression is so extreme that the rules governing the water no longer apply inside the glass, and the size problem cuts both ways. Not only is the mass extraordinary for such a small space, but the way we detected it, by watching stars orbit around it, tells us the mass must be concentrated at a single point. If the mass were spread out even slightly, the orbital paths of the surrounding stars would look different. The fact that they follow such precise elliptical paths around a tiny central location means the mass is genuinely concentrated there, in a space incomprehensibly small. Here is what makes this stranger still. Sagittarius A star is considered a relatively modest, supermassive black hole. There are black holes at the centers of other galaxies with masses billions of times greater than our star. The one at the center of the galaxy Messier 87, the first black hole ever directly photographed, is roughly 6.5 billion times the mass of our star, and it sits in a region no proportionally larger than our own galactic center. These objects exist, we have confirmed that. What we have not confirmed is how they form. How a black hole grows to 4 million or 4 billion solar masses is one of the deepest unsolved problems in astrophysics. The timescales involved, the mechanisms of growth, and the conditions required, none of it matches current models perfectly. So the mass problem is not just about Sagittarius A star, it is about whether our understanding of how galaxies grow and evolve is fundamentally incomplete. And there is one clue sitting right next to the black hole, close enough to touch it by cosmic standards, that suggests our models may be missing something crucial. Something is orbiting that black hole right now at speeds that should be impossible to survive. Right now, a cluster of massive young stars is circling the most powerful gravitational object in our galaxy at speeds that challenge everything we know about stellar physics. These are the stars, and they should not be there. There are roughly 24 of them confirmed so far, packed into a region only a fraction of a light year across, practically on top of Sagittarius A star by cosmic standards. They orbit the black hole the way planets orbit a star, except the central object is 4 million times more massive, the orbital speeds are far greater, and the environment surrounding them would strip apart anything less resilient. The star called STU has become the most studied individual star in the history of astronomy. Over the decades that researchers have tracked it, STU completes a full orbit of the black hole every 16 years. At its closest approach, it swings within roughly 17 light hours of Sagittarius A star, traveling at nearly 3% of the speed of light. That is close to 20 million miles per hour. To put that in perspective, a fighter jet flying at full speed would take roughly 400,000 years to cross the distance between our star and its nearest neighboring star. STU crosses a comparable distance in days. At these speeds, and at this closeness to such a massive object, the effects of general relativity become measurable. Light from STU shifts toward the red end of the spectrum as it climbs out of the black hole's gravity well. Time itself ticks slightly differently near the black hole compared to farther out. These are confirmed observations. STU has become a living laboratory for testing Einstein's predictions in one of the most extreme environments accessible to us. But here is what no one has explained satisfactorily. These stars are young, not ancient relics from the galaxy's early history. Young, hot, massive stars that formed recently within the last few million years. And forming a star requires enormous clouds of cold gas to gradually collapse under their own gravity over millions of years. Near a supermassive black hole, that process cannot happen. The gravitational tidal forces near Sagittarius A star are so intense that they would shred any gas cloud before it could collapse into a star. The environment is too violent, too turbulent, too extreme for the slow, delicate process of star formation to occur. The physics simply does not allow it. So, how are these young stars there? Astronomers call this the paradox of youth. 3 leading theories have been proposed. One suggests the stars formed farther out and were dragged inward by some gravitational mechanism we do not fully understand. Another proposes they formed in an exceptionally dense disk of gas around the black hole, under conditions that bypassed normal star formation rules. A third suggests they were part of binary star systems that were torn apart by tidal forces, leaving one star captured in a close orbit while the other was flung outward. None of these explanations is confirmed. All of them require conditions or mechanisms that push the edges of current physics. The stars exist, their youth is measured and real, and our best models cannot account for how they got where they are. But the stars themselves are only the beginning of what surrounds Sagittarius A star, because the black hole itself has started doing something that nobody predicted, and it is doing it randomly. On most days, Sagittarius A star is quiet. It emits a low, steady hum of radiation, mostly in radio waves and X-rays, consistent enough that astronomers have used it as a baseline measurement for decades. Then, without warning, it erupts. Not in the way you might picture an explosion. There is no shockwave, no fireball expanding outward. What happens is more subtle, and in some ways, more unsettling. The black hole suddenly blazes dozens of times brighter than its normal state, pouring out bursts of infrared light and X-ray radiation that can last anywhere from a few minutes to a few hours. Then it dims again, back to the baseline, as if nothing happened. These are called flares, and they occur multiple times per day, every day, reliably, repeatedly, and completely unpredictably. The first confirmed flares from Sagittarius A star were detected in the early 2000s using the Chandra X-ray Observatory, a telescope in orbit above Earth's atmosphere operated by the National Aeronautics and Space Administration, capable of seeing forms of light invisible to ground-based instruments. What Chandra captured was sudden, dramatic, brightening at the galactic center, spikes of energy that shot up and then faded in patterns too fast to be explained by anything we had modeled for this region. What causes them? This is an active area of research, and no single explanation has won consensus. One leading idea is that small clumps of gas or dust occasionally spiral close enough to the black hole to heat up violently before crossing the point of no return. As the material falls inward, it accelerates, heats to millions of degrees, and releases a burst of radiation before disappearing. Think of it like a log dropping into a fire, producing a brief spike of heat and light before the embers settle. Another theory involves magnetic reconnection. Near the black hole, magnetic field lines are constantly tangled and under enormous stress. When two opposing field lines snap and reconnect, they release enormous amounts of energy almost instantaneously, similar to the process that drives flares on our own star, though at vastly greater scales and intensity. A third possibility involves something orbiting just outside the black hole at extraordinary speed. As material races around the innermost stable orbit, it may form hotspots that temporarily concentrate radiation in our direction, producing what we perceive as a flare. All 3 mechanisms are physically plausible. All 3 may be happening simultaneously, and none of them has been isolated as the definitive cause. What makes the flare problem particularly interesting is that the brightest flares observed from Sagittarius A star have grown significantly more powerful in recent years. In 2019, the black hole produced the brightest flare ever recorded from this source. It was roughly 75 times its normal brightness. Researchers are still studying whether this represents a genuine increase in activity or simply better instrumentation catching events that were always occurring. Either answer changes our understanding of the galactic center. If The black hole is genuinely becoming more active. Something has changed in its feeding environment. If we were simply missing flares before, then our previous model of Sagittarius A star as a calm object was always wrong. Both possibilities suggest we are missing something fundamental about what drives behavior in the most powerful object in our galaxy. And the flares are only one of several ways the galactic center is defying prediction. The magnetic field surrounding it is doing something the models cannot account for either. Magnetic fields exist everywhere in the universe. Around planets, through stars, threading between galaxies in faint, invisible strands. Most of the time they are weak, diffuse, and manageable within our current models. At the center of the Milky Way, the magnetic field is something else entirely. Measurements taken over the past 2 decades have revealed that the magnetic field near the galactic center is somewhere between 1,000 and 10,000 times stronger than the average field in the rest of the galaxy. This is not a small discrepancy. This is an order of magnitude problem, and in some places, several orders of magnitude. The field is so powerful that it influences the movement of gas and plasma across enormous distances, channeling material in ways that defy the behavior seen in other regions of space. What is making it this strong? That is an open question with no confirmed answer. In most environments, magnetic fields of this intensity would require either a sustained source of energy to maintain them, or a physical process that keeps regenerating them faster than they naturally decay. Neither mechanism is clearly identified at the galactic center. One theory connects the field to the activity of Sagittarius A star itself. As gas spirals toward a black hole, it can generate and amplify magnetic fields through a process called a dynamo effect, similar to how Earth's liquid iron core generates our planet's magnetic field by rotating. If the black hole has been pulling in magnetized material over billions of years, it may have built up an extraordinary field in the surrounding region. Another possibility involves the dense population of massive stars near the galactic center. Massive stars have strong magnetic fields of their own, and when they die in supernova explosions, they release those fields into the surrounding medium. With so many massive stars crowded into such a small region, the combined contribution could be adding up over time. A third idea, less developed but worth noting, is that the field is a relic from the early universe, a leftover from the conditions that shaped the Milky Way in its first billion years, simply preserved and concentrated near the galactic center by the intense gravity there. None of these explanations has been ruled out. None has been confirmed. What makes the magnetic field anomaly particularly significant is its effect on everything else at the galactic center. Magnetic fields, this powerful, do not just sit passively in space. They act on charged particles, shaping their paths, concentrating them, accelerating them. The flares we discussed may be partly driven by the field's behavior. The strange filaments of radio emission we will encounter later are almost certainly connected to it. The field is not just a curiosity. It may be central to why the galactic center behaves so differently from anything our models predict. Consider what it means to have a magnetic force field 1,000 times stronger than the background level of our galaxy wrapped around the most massive object in the Milky Way. Every charged particle within that region, every electron, every proton, is being steered by it. The region becomes something like a particle accelerator on a galactic scale. And then, above and below the entire galaxy, reaching tens of thousands of light years into space, the consequences of everything happening at that core become visible in a way nobody saw coming. What researchers found next was so large it had been hiding in plain sight for decades. In 2010, astronomers analyzing data from the Fermi Gamma Ray Space Telescope made a discovery so large it seems almost impossible to have missed. Stretching above and below the flat disk of the Milky Way, 2 enormous lobes of energy were erupting outward from the galactic center. Each one extends approximately 25,000 light-years from the plane of the galaxy. Together, they span roughly half the width of the entire Milky Way. They are called the Fermi Bubbles, and they are one of the most significant discoveries in galactic astronomy in recent memory. To appreciate their scale, consider that our entire solar system, including the outer reaches of the cloud of icy bodies surrounding it, spans roughly 1 to 2 light-years. The Fermi Bubbles are 25,000 times taller than that on each side. They are not a feature of the inner galaxy. They are a feature of the entire galaxy. And they were hidden in the data for years because nobody had thought to look for something that large. What is inside them is a soup of high-energy gamma rays, X-rays, and charged particles called cosmic rays, all moving outward from the galactic center at significant fractions of the speed of light. The edges of the bubbles are surprisingly sharp, which tells astronomers the expanding energy is being contained by something rather than simply dissolving into surrounding space. That sharpness is itself not fully explained. What caused them is an active mystery. The two leading explanations point in different directions. One proposes that Sagittarius A star was once far more active than it is today. Millions of years ago, it may have entered a quasar-like phase, consuming enormous amounts of material and blasting jets of energy perpendicular to the galactic disk. Those jets would have inflated the bubbles over hundreds of thousands of years before the black hole quieted down to its current restrained behavior. This is a theory. It fits some observations, but requires Sagittarius A star to have been orders of magnitude more active in the past than it is now. The second explanation attributes the bubbles to a period of intense star formation near the galactic center, a starburst event where stars formed rapidly, lived short, violent lives, and died in cascading supernova explosions that collectively launched a wind of energy outward. This wind, sustained over millions of years, could have inflated the bubbles gradually. This is also a theory. It fits different aspects of the observations and has different problems from the first. Some researchers believe both events happened and contributed. Others think a third unknown process is responsible for at least part of what we see. What is confirmed? The bubbles are real. They are enormous. They are filled with high-energy particles, and they are connected to the galactic center. Their sharp boundaries suggest they are still actively being maintained, or that they are much younger than originally assumed. Either way, the Fermi Bubbles change how we understand the Milky Way. For most of human history, we pictured our galaxy as a flat disk of stars rotating calmly through space. The galaxy has lobes. It has structure above and below the disk on a scale that dwarfs the visible galaxy itself. And in the very center of the structure that produced them, below the galactic plane and above it, are mysteries still piling up, including one that is personal, because the next anomaly is not about what lives near the black hole. It is about what should not be able to live there at all. The stars we encountered earlier were already difficult to explain, but they are part of a broader problem that runs deeper through the galactic center. There are young stars scattered throughout the inner few light years of the galaxy, and the more carefully astronomers look, the more they find. Some of these stars are arranged in what appears to be a disk, rotating around Sagittarius A star in a coherent plane. Others seem randomly distributed with no clear orbital pattern. Some are moving clockwise, some counterclockwise. The situation is messy, and that messiness is precisely what makes it scientifically alarming. In the calm regions of the galaxy where we live, stars form in giant molecular clouds, vast reservoirs of cold gas that gradually accumulate mass, cool down, and eventually collapse under gravity to ignite nuclear fusion. This process takes millions of years. It requires stability. It requires the gas to remain cool and coherent long enough for gravity to win. Near the galactic center, none of those conditions apply. The gas near Sagittarius A star is being stirred constantly by tidal forces, radiation pressure, magnetic fields, and the gravitational influence of hundreds of other massive objects. The temperature of the gas is far higher than in the calm outer galaxy. The turbulence is extraordinary. Any gas cloud attempting to collapse into a star would be pulled apart before it got halfway there. This is not speculation. The mathematical threshold below which tidal forces from Sagittarius A star overwhelm the self-gravity of a gas cloud is well established. It is called the Roche limit, and everything within roughly 6 light-years of the black hole falls inside it. Clouds within that boundary should not be able to form stars, and yet they did, relatively recently. The stars we see near the galactic center are not billions of years old. Many of them are only a few million years old at most, barely an eye blink in cosmic time. If they formed somewhere else and migrated inward, we would expect their orbits to show signs of that journey. Many of them do not. They look like they formed where they are. One of the most compelling explanations involves a gas cloud of unusual density that fell toward the galactic center on a nearly radial path. As it compressed during infall, the densest pockets of gas may have reached the threshold for stellar ignition before tidal forces could shred them, a race between collapse and destruction that these particular clouds happened to win. This is a theoretical model, not a confirmed event. Another idea involves the disk of gas that may have once surrounded Sagittarius A star at much higher density than today. In the innermost, most compressed region of such a disk, temperatures and densities could create conditions unlike anything in normal star-forming regions, conditions where normal rules bend. What compounds the mystery is scale. The young stars near the galactic center are not a handful of anomalies. There are enough of them to suggest that whatever process formed them has operated multiple times. There may be ongoing star formation happening at the galactic center right now, in a region our textbooks say should be sterile. The universe appears to have found a way around the rules again, and the rules keep getting broken, because while stars are appearing where they should not be, there is something else near the galactic center that is conspicuously absent, something that every model predicts should be there in enormous numbers. It simply is not. When astronomers build computer models of how stars distribute themselves around a supermassive black hole, the predictions are consistent and clear. Gravity works in a straightforward way over large distances. The closer you get to the black hole, the more stars there should be, pulled inward by the immense gravitational well at the center. The density of old stars, the ancient population of faint red and orange stars that have been accumulating near the galactic center for billions of years, should increase steeply as you approach Sagittarius A star. The mathematical peak of this density is called the stellar cusp. It is not there. When astronomers actually look at the distribution of old stars near the galactic center, the expected cusp is absent. Instead of increasing steeply toward the center, the density of old stars flattens out and even drops in the very innermost region. The old stars are missing from precisely the place where they should be most numerous. This is known as the missing cusp problem, and it has been an active puzzle in galactic astrophysics since the 1990s. Several explanations have been proposed, and each one carries significant implications. One possibility is that the old stars were destroyed. A black hole of Sagittarius A star's mass can tear apart stars that venture too close, an event called a tidal disruption. Over billions of years, any star that strayed into the innermost region would eventually be consumed. If the rate of consumption has been high enough over the age of the galaxy, the inner population could have been significantly depleted. A second explanation involves the orbits of the stars themselves. Gravitational interactions between stars and between stars and the black hole can gradually scatter orbital paths over time. Stars that start in tight inner orbits may be kicked outward over millions of years by these repeated close encounters. If this process has been efficient enough, the innermost region may have been slowly emptied of its residents. A third possibility is more radical. Some researchers have proposed that a dense cluster of compact objects, black holes, neutron stars, and white dwarfs, the dead remnants of the massive stars that lived and died near the galactic center, might be providing a gravitational influence that pushes the surviving ordinary stars outward. This invisible inner population would not show up in optical or infrared surveys, making it effectively invisible to most of our instruments. None of these explanations fully accounts for the observed distribution. Some models that fit the missing cusp create other problems elsewhere in the predicted stellar environment, and the data itself has been difficult to gather, because looking at individual faint old stars in one of the most crowded and cluttered regions of the sky is extraordinarily challenging. What the missing cusp tells us, regardless of its cause, is that something has been actively reshaping the population of stars near the galactic center over billions of years. The core of our galaxy is not a passive gravitational well-collecting material. It is an environment that has been processing, consuming, ejecting, and rearranging its contents continuously. The history written in the positions of these missing stars is one of a violent, turbulent place where the expected outcomes rarely match the actual ones. And the strangeness does not stop with the stars we cannot find. Stretching across the galactic center in patterns nobody predicted are structures we still cannot explain, and they are among the most bizarre things in the observable universe. In the 1980s, radio astronomers mapping the inner galaxy began noticing something strange running through the galactic center. Thin, elongated structures of radio emission, stretching vertically out of the galactic plane like threads pulled tight. Each one narrow, remarkably straight, and glowing in radio wavelengths with an intensity far above the surrounding background. They named them non-thermal radio filaments, and the more they looked, the more they found. Today, we know of hundreds of them. They range in length from a few light years to over 100 light years. Most run roughly perpendicular to the galactic plane, oriented vertically rather than horizontally, which immediately sets them apart from most other structures in the galaxy. They do not clump together randomly. They appear in patterns, sometimes in parallel groups, sometimes isolated, and the pattern itself has never been satisfactorily explained. What are they? After decades of study, the answer is still unclear. The most widely accepted explanation involves the strong magnetic field at the galactic center. Electrons moving at near-light speeds, called relativistic electrons, spiral along magnetic field lines and emit radio waves through a process called synchrotron radiation. The filaments may be regions where the galactic magnetic field is locally concentrated and aligned, creating channels where these fast-moving electrons naturally accumulate and radiate. This is the leading theory. It fits the physics of how magnetic fields and relativistic particles interact, but it raises its own questions. Where are the relativistic electrons coming from? Producing electrons at these speeds requires significant energy input, far more than the background radiation of the galaxy can supply. Something near the galactic center must be continuously accelerating particles to these energies. Sagittarius A star is the obvious candidate, but the connection between the black hole's modest current activity and the energy needed to sustain hundreds of filaments has never been established with certainty. Some filaments appear to be interacting with gas clouds, which suggests they are physical structures embedded in the material of the galactic center, rather than just projections of magnetic fields along our line of sight. A handful of filaments show evidence of heating the gas around them, implying they carry real energy, not just the appearance of it. A new discovery added another layer in 2022. A team using the Meerkat radio telescope in South Africa produced the most detailed radio image of the galactic center yet assembled. In that image, hundreds of previously unknown filaments appeared, including a class of shorter, more horizontal structures that do not match the vertical pattern of the classic filaments at all. These newer structures have orientations and lengths inconsistent with the standard magnetic explanation. Two distinct populations of filaments, two potentially different origins, both unexplained. The galactic center, seen in radio waves, does not look like the interior of a galaxy. It looks like something has been drawing across it with enormous brushstrokes of energy, leaving trails that persist across thousands of years. What those brushstrokes represent, what force or event drew them, and why they have the shapes and orientations they do, remains an open problem in one of the most actively studied regions of the sky. Go deeper still, and the region itself is moving in a direction the orbital rules of our galaxy cannot account for. And that movement has been baffling researchers for longer than most people realize. Our galaxy rotates. Every star, every cloud of gas, every cluster of dust traces an orbit around the galactic center, carried along by gravity in a slow, majestic circulation that takes our own star roughly 230 million years to complete. The general rule is elegant. Things closer to the center orbit faster, things farther out move more slowly. Gas and stars follow nearly circular paths, maintaining a kind of ordered flow. The 3 kiloparsec arm does not follow the rule. Located roughly 10,000 light-years from the galactic center, this enormous structure of gas is moving in a direction that defies the normal orbital pattern of the galaxy. Instead of following a roughly circular path around the center, the gas in this feature is expanding outward, moving away from the galactic center at around 135 miles per second. This is not a slight deviation. This is a stream of gas the size of a galactic arm being actively expelled from the center of the Milky Way, and it is happening on both sides simultaneously. There is a near side, 3 kiloparsec arm moving toward us, and a far side counterpart on the other side of the galaxy moving away from us. Together, they form a symmetric expanding structure, which strongly suggests a single central event drove both of them outward at the same time. When was that event? The size of the arms and their current velocity, run backward through time, suggest the expansion began somewhere between 30 and 80 million years ago. That is a wide window of uncertainty, reflecting how difficult it is to model the complex dynamics of gas in the inner galaxy over geological timescales. What produced this expansion? This is where the debate intensifies. One camp points to Sagittarius A star. If the black hole went through a period of intense activity sometime in the past, it could have launched jets or driven winds powerful enough to push enormous quantities of gas outward over millions of years. The symmetry of the two arms supports this, since jets from a black hole typically fire in opposite directions along the rotation axis. Another explanation involves the galactic bar. The Milky Way is not a simple spiral. It has a bar-shaped structure of stars running through its center, and the gravitational resonances created by this rotating bar can drive gas into unusual, non-circular orbits. The 3 kiloparsec arm may be a result of bar-driven dynamics, with gas being captured into specific resonant orbits that give it the appearance of expansion when it is actually following a complex gravitational path. A third possibility combines both: a bar-driven orbit that was amplified or displaced by a period of elevated activity from the central black hole. None of these explanations is confirmed. All of them require either a past event we cannot directly observe or a dynamical mechanism we cannot yet fully simulate. What is confirmed is the structure itself, a massive ribbon of gas moving at speeds inconsistent with ordinary rotation, expanding outward from the galactic center, symmetric on both sides, telling us something dramatic happened at the heart of our galaxy within the last 100 million years. That something left its fingerprints in the gas and also in the very shape of the galaxy itself. Because our galaxy has a feature that influences everything else at the center, including the gas, the stars, and possibly the black hole. And that feature has only recently been studied in detail. For most of the 20th century, The Milky Way was depicted as a classic spiral galaxy, a graceful pinwheel of stars with arms curving outward from a central hub. This image appeared in textbooks, documentaries, and science museum displays for generations. It was reasonable, based on the best available data. It was also incomplete. We now know that at the center of the Milky Way, cutting through the nucleus, is a bar, a thick, elongated structure of stars, gas, and dust stretching roughly 27,000 light-years from end to end, oriented at an angle to the spiral arms. It is not a minor feature. It is fundamental to the structure of the entire galaxy. Barred spiral galaxies are actually common. Surveys of other galaxies suggest that somewhere between 60 and 70% of all spiral galaxies, confirmed, have bars. Our own galaxy joining this category is understandable in retrospect. Still, understanding what the bar does to the inner galaxy, including the region surrounding Sagittarius A star, remains an active area of research. Here is the key problem. A rotating bar is not just a passive structure. It acts like a gravitational stirring rod, sending ripples of resonance through the surrounding material as it spins. Gas clouds, stellar orbits, and dust lanes all respond to the bar's gravitational influence. The bar creates regions where orbits become unstable, where gas can pile up or be driven inward, and where the normal circular flow of galactic rotation breaks down. The most significant of these effects involves gas funneling. As the bar rotates, it herds gas along its length and channels it toward the galactic center. This process is confirmed in computer simulations and is consistent with what we observe. Over millions to billions of years, the bar effectively feeds material toward the inner galaxy, delivering gas that could fuel star formation near the center or eventually find its way towards Sagittarius A star itself. This may explain why the galactic center shows signs of recent and ongoing activity, despite being far from the nearest large reservoir of gas in the outer galaxy. The bar is a pipeline. But the bar also complicates the dynamics at the galactic center in ways that are harder to model. The resonances it creates can produce non-circular orbits, like the 3 kiloparsec arm we discussed in the previous chapter. It can drive the formation of rings of gas at specific distances from the center. It may influence the rate at which material falls toward the central black hole, alternately starving it and feeding it over timescales of millions of years. What is the bar's current effect on Sagittarius A star? The honest answer is we do not know precisely. The timescales of bar dynamics are long, the distances involved are enormous, and our ability to model the combined gravitational influence of a 4 to million solar mass black hole, a 27,000 light-year bar, and billions of individual stars simultaneously is limited by the complexity of the calculation. What we can say is this: the galactic center is not an isolated environment. It is embedded in and continuously influenced by the large-scale structure of the entire galaxy. The bar, the spiral arms, the surrounding gas reservoirs, all of them are connected to what happens at the core. And what happened at the core in the past has left a record written in something other than visible light, something that has been bouncing through the galaxy for centuries. The galactic center is not just a place to observe in the present, it is a place where the past is still arriving. Light takes time to travel. When something bright happens at the galactic center, the light from that event does not reach every object in the surrounding region simultaneously. Clouds of gas positioned at different distances from the source receive the light at different times, and when that light is powerful enough, it causes those gas clouds to glow in response, re-emitting the energy in X-rays. This is the phenomenon called X-ray echoes, or light echoes, and at the galactic center, it is giving us a window into events that happened centuries or even millennia ago. Here is how it works. Suppose Sagittarius A star produced a powerful burst of X-ray radiation at some point in the past. That burst traveled outward in all directions. Some of it went directly toward Earth, and depending on when it happened, may have already passed us by. But some of it traveled sideways first, hit a gas cloud at an angle, and is only now being reflected toward us. By measuring the position and brightness of the glowing cloud, astronomers can calculate when and how powerful the original burst was. What they have found using this technique is startling. Several large molecular clouds near the galactic center have been observed brightening and fading in, X-rays over periods of years to decades. The most studied of these is a cloud called Sagittarius B2, one of the largest and densest molecular clouds in the Milky Way, located about 300 light-years from Sagittarius A star. It has shown significant X-ray brightening consistent with being illuminated by a past burst from the galactic center. Working backward through the geometry of the echo, researchers have estimated that Sagittarius A star produced a burst of X-ray luminosity roughly 200 to 400 years ago that was somewhere between 1 million and 100 million times brighter than its current output. The uncertainty in that estimate is large, but even the lower end of the range represents an event vastly more energetic than anything seen from the black hole in modern observations. This is a theory consistent with multiple independent lines of evidence. It is not yet confirmed at the level of certainty that would satisfy all researchers. But if it is correct, the implications are significant. It means Sagittarius A star was not always as quiet as it appears today. It has had episodes of dramatically increased activity, possibly related to the consumption of a large cloud of gas or the disruption of a star that passed too close. The black hole we observe today may be in a temporary lull between periods of much greater brightness. The echoes also tell us something about the structure of the material surrounding the galactic center. The way X-rays propagate through and reflect off different clouds maps the three-dimensional distribution of dense gas in the region, information that is otherwise very difficult to obtain. We are essentially using the black hole's past behavior as a flashlight, illuminating the structure of the surrounding environment with light that left its source centuries before any living person was born. The past is still traveling toward us, and what it is revealing about this region keeps getting stranger, because scattered through the galactic center are objects that should not survive their proximity to the black hole. Yet they do, and nobody fully understands why. In 2009, physicists analyzing data from the Fermi Gamma-ray Space Telescope noticed something unexpected layered on top of everything else coming from the galactic center: a diffuse glow of gamma rays, not the sharp energetic bursts associated with known sources like pulsars or supernova remnants. A smooth, extended haze of radiation centered precisely on Sagittarius A star and spreading outward in a roughly spherical pattern for thousands of light years. It has become known as the galactic center gamma XS, and it has resisted explanation for over 15 years. The glow involves gamma rays in the high energy range of billions of electron volts, a level associated with extreme physical processes. The signal is real. It has been confirmed by multiple independent teams using different analysis methods on the same underlying telescope data. Whatever is producing it is genuinely there. But what is it? The first candidate explanation, and the one that generated the most scientific excitement, is dark matter annihilation. Dark matter is the invisible substance that makes up roughly 27% of the total mass energy content of the universe, confirmed by its gravitational effects on galaxies and large-scale structure, but never directly detected. One class of dark matter candidate particles, called weakly interacting massive particles, is predicted to produce gamma rays when two of them collide and annihilate each other, converting their mass directly into energy. The galactic center is the densest concentration of dark matter in the Milky Way. If dark matter particles are colliding anywhere, they should be colliding most frequently right there. And the energy spectrum of the observed gamma ray excess matches reasonably well with what certain dark matter annihilation models predict. This is a theory. It has not been confirmed. The problem is that a second explanation fits the data equally well. Millisecond pulsars are ancient, rapidly spinning neutron stars that emit gamma rays in a particular energy range. The galactic center is crowded with old, evolved stars, and old stars produce neutron stars when they die. If the galactic center contains a large population of millisecond pulsars too faint to detect individually, their combined emission could produce exactly the kind of smooth, diffuse gamma-ray glow that has been observed. Later analyses found statistical hints that the glow might be composed of many point sources rather than truly diffuse emission, which would support the millisecond pulsar explanation. But the resolution of the telescope is not sufficient to definitively resolve the glow into individual sources, leaving the question open. A third possibility involves cosmic rays, high-energy charged particles, interacting with dense gas clouds in the galactic center region to produce gamma rays through a process called pion decay. The galactic center has plenty of both cosmic rays and dense gas. Whether this process can account for the full observed excess or only part of it is still being calculated. 3 plausible explanations, none confirmed. The galactic center gamma excess remains one of the most debated anomalies in high-energy astrophysics. What makes it matter beyond academic curiosity is the dark matter possibility. If that explanation proves correct, it would be the first direct detection of dark matter in the history of science. It would answer one of the most fundamental questions in physics about what most of the universe is made of. The stakes are extraordinary. The signal is real. The source is unknown, and what might be producing it could be stranger than any of the current explanations suggest. Dark matter is one of the most unsettling concepts in modern science. We know it exists. We have no idea what it is. The evidence for dark matter is not subtle. Galaxies rotate in ways that cannot be explained by the visible matter they contain. Stars at the outer edges of spiral galaxies move just as fast as stars near the center, which should be impossible if gravity were only coming from the stars, gas, and dust we can see. Something invisible is providing additional gravitational pull. That invisible something is dark matter. It accounts for roughly 5 times more mass than all the ordinary matter in the universe combined. Every galaxy, including our own, is embedded in a vast halo of it, and the densest concentration of dark matter in the Milky Way sits right at its center, around and beneath Sagittarius A star. This makes the galactic center the most promising location in the observable universe to search for direct evidence of what dark matter actually is. The leading theoretical candidate for dark matter is a class of particles called weakly interacting massive particles. These particles, if they exist, would interact with ordinary matter only through gravity and the weak nuclear force, making them invisible to light and almost impossible to detect directly. But there is one situation where they would produce a detectable signal when 2 of them meet and annihilate each other. When a weakly interacting massive particle and its antiparticle collide, they convert their combined mass entirely into energy, producing gamma rays at a specific and predictable energy level. The exact energy depends on the mass of the particle, and different theoretical models predict different masses. But many of those predictions fall squarely in the range of the galactic center gamma excess we discussed in the previous chapter. The match between the predicted signal from dark matter annihilation and the observed gamma ray excess is not perfect. It is suggestive. Scientists are careful to call it a hint rather than evidence, and cautious to call it evidence rather than confirmation. What makes the case complicated is the sheer difficulty of the environment. The galactic center is filled with known sources of gamma rays, pulsars, supernova remnants, cosmic ray interactions, and the general turbulent activity of the region. Separating a faint, diffused dark matter signal from all of those competing sources requires extraordinarily precise modeling of every other contribution, and the models themselves carry uncertainties. Independent searches for dark matter annihilation have been conducted using observations of dwarf satellite galaxies orbiting the Milky Way, regions with almost no conventional astrophysical activity and therefore much cleaner backgrounds. So far, those searches have produced no confirmed signal. This does not rule out the galactic center excess as a dark matter signal, because the density of dark matter in dwarf galaxies may simply be too low to produce a detectable effect. But it does mean the case remains open. What is at stake here extends far beyond the galactic center. If the excess is eventually confirmed as dark matter annihilation, it would not just solve a local puzzle. It would be the first time in human history that we directly observed the most abundant form of matter in the universe. The galactic center may be, right now, silently annihilating the substance that built the large-scale structure of the cosmos. Or it may be doing something else entirely, because not everything near the black hole that defies expectation is invisible. Some of the strangest objects are ones we can see clearly, and they have been surviving in ways that should be physically impossible. In 2012, astronomers observing the galactic center noticed something moving towards Sagittarius A star that did not fit neatly into any existing category. It looked like a cloud of gas and dust in some wavelengths. It behaved like a star in others. It was compact enough to hold together under tidal stress that would have shredded an ordinary gas cloud, yet diffuse enough to show the spectral signatures of gas rather than a solid stellar surface. They called it GONE, for lack of a better name. When researchers tracked its trajectory and realized it was heading directly towards Sagittarius A star on a close approach orbit, predictions flew quickly. Many expected the object to be torn apart as it rounded the black hole, producing a dramatic feeding event and a significant brightening of Sagittarius A star. Observatories around the world prepared to watch. In 2013, GONE made its closest approach to the black hole, passing within a few hundred times the distance from our planet to our star. It survived. Sagittarius A star barely responded. Nobody had expected that. As researchers puzzled over GONE, a second object was found nearby. G2 followed a similar type of orbit and was also approaching Sagittarius A star. It made its closest approach in 2014, even closer than GONE. It also survived, stretching and distorting in the black hole's gravitational field, but never fully breaking apart. Again, the black hole showed no significant increase in activity. Today, we know of at least 6 of these objects, collectively called G objects, all orbiting within the inner fraction of a light year of Sagittarius A star. What are they? The current leading theory, still under active debate, is that they are the result of stellar mergers. In the dense environment near the galactic center, 2 stars in a binary system can be driven together by gravitational interactions, merging into a single bloated object surrounded by an envelope of gas and dust. The merged star would be compact enough internally to resist tidal disruption, while the surrounding gas envelope would give it the diffuse appearance that distinguishes it from an ordinary star. This is a theory. The data support it more than any other current explanation, but it has not been definitively confirmed. What the G objects demonstrate, regardless of their precise nature, is that the region immediately surrounding Sagittarius A star harbors object types that do not appear in any other well-studied astronomical environment. The extreme conditions near the black hole appear to be producing things that our existing categories cannot cleanly accommodate. A gas cloud that acts like a star that survived a close pass to a 4 to million solar mass black hole. Objects that exist in the boundary between categories that our physics had assumed were distinct. These objects are also providing a real-time test of how matter behaves in extreme gravitational fields. Every orbit they complete is data that constrains our models of the environment closest to the black hole. But even the G objects, strange as they are, represent individual anomalies. What comes next is an anomaly that operates at the level of the entire population of stars near the galactic center, and it involves something that challenges a foundational assumption about how orbital mechanics works. Some things near the black hole are going the wrong way, and not just a few of them. When the stars were first mapped in detail, researchers expected to find them orbiting Sagittarius A star in a single coherent plane, moving in the same direction. Gravity typically organizes things this way: a cloud of material that collapses, or a stream of gas that spirals inward, tends to flatten into a disk and rotate in one direction, the way our solar system's planets all orbit in roughly the same plane and the same direction. What they found was the opposite of organized. Some of the stars orbit clockwise when viewed from a particular direction. Others orbit counterclockwise in the same view. Some orbit in a plane that is tilted steeply relative to the galactic disk. Others orbit in planes inclined at completely different angles. Rather than a single coherent disk, the innermost stellar population near Sagittarius A star appears to contain at least two distinct disk-like structures with opposite orbital orientations, plus a population of stars that do not fit neatly into either disk. This counter-rotating structure is one of the most puzzling features of the galactic center. In most scenarios of disk formation, material settles into a single dominant rotation direction because angular momentum from the original source material tends to be uniform. For two disks rotating in opposite directions to coexist around the same object, two separate infall events must have occurred, each bringing material with angular momentum oriented in a different direction, and both events must have deposited enough stars to remain detectable today. This is theoretically possible. The galactic center is a violent, dynamic environment that has been accreting material from multiple directions over billions of years. A massive gas cloud falling in from one direction could produce one disk of stars. A later cloud falling in from a different, roughly opposite direction could produce the second. The timing and geometry would need to line up in a specific way, but it is not forbidden. What remains unexplained is why the disks are still as distinct as they appear to be. Over millions of years, gravitational interactions between stars and between stars and the black hole should gradually randomize orbital orientations, smearing any initial disk structure into a more uniform distribution. The fact that we can still identify distinct prograde and retrograde populations suggests either that the infall events were relatively recent, or that some mechanism is maintaining the distinction longer than standard models would predict. There is also a third population, stars that do not belong to either disk, with orbital inclinations scattered across a wide range of angles. These may be the oldest residents of the region, their original disk memberships long since erased by gravitational scattering, or they may represent a third, older infall event that has been more thoroughly randomized than the two younger disks. What the counter-rotating disks tell us is that the galactic center has had a complex, multi-episode history of acquiring stars from different directions at different times. It is not a simple, steady-state system. It is the product of repeated events, each leaving its own partial imprint on the stellar population. And, with each layer of complexity we add to the picture, the environment near the black hole becomes less like a place where ordinary physical intuitions apply, and more like a place where everything familiar bends. Some of that bending is literal. What tidal forces do to anything that ventures too close to Sagittarius A star would be among the most extreme experiences physically possible in this universe. Imagine you are falling towards Sagittarius A star, not the whole journey, just the final approach, close enough that the black hole fills your perception of space completely. You would not feel heat first, or radiation, or the crushing pressure of a collapsing star. What you would feel first, and what would kill you long before anything else, is stretching. Tidal forces are the difference in gravitational pull across the width of an object. On Earth, the difference in the Moon's gravitational pull between your feet and your head is tiny, unmeasurably small in everyday life. Near a sufficiently massive object, that difference becomes enormous. An object falling toward a black hole experiences a pull on its near side that is dramatically stronger than the pull on its far side. The result is elongation along the direction of fall. In the literature, this process has a name that is both precise and vivid: spaghettification. For a human body falling towards Sagittarius A star, the tidal forces would become lethal at a distance of roughly tens of millions of miles, far outside the event horizon. You would be stretched into a thin filament of matter long before crossing any point of no return. For larger objects, the situation is more complex. A star falling toward the black hole would begin to distort when it crossed the tidal disruption radius. For Sagittarius A star's mass, that radius is actually inside the event horizon for typical stellar masses, which means a whole star could cross into the black hole without being fully disrupted first. This is one reason Sagittarius A star may be less active than expected. The stars that fall into it may disappear cleanly rather than being torn apart into a glowing accretion disk. For gas clouds and lower mass objects, tidal disruption happens outside the event horizon. The cloud is stretched into long filaments, some of which fall inward and some of which are flung outward in highly elongated orbits. This process, when it involves a star, is called a tidal disruption event and produces a characteristic burst of radiation that can briefly outshine the entire host galaxy. Tidal disruption events have been observed in other galaxies. Though detecting one close to a supermassive black hole is extremely challenging, several candidate events have been identified near Sagittarius A star using X-ray and infrared data, but the crowded environment of the galactic center makes confirmation difficult. What makes tidal forces especially important in the context of the galactic center mysteries is their role in everything else we have discussed. The missing cusp, the paradox of youth, the G objects surviving close passes, the disruption of binary stars that may produce the star population. Tidal forces are the underlying mechanism connecting all of these phenomena. The black hole does not need to actively reach out and destroy things. It simply needs to be massive and compact, and gravity does the rest. Objects that approach too closely are reshaped, disrupted, consumed, or flung away. The galactic center is a place where the geometry of space-time itself becomes a hazard. And somewhere at the very center of that geometry sits a black hole that, for all its power, is consuming far less material than it should. That restraint is one of the deepest puzzles of all, because by everything we know about how black holes feed, Sagittarius A star should be roaring, and it is barely whispering. Sagittarius A star is the most massive object in the Milky Way. It sits at the center of the most energetic region in the galaxy. It is surrounded by gas, dust, and stars at densities far greater than anywhere else in the Milky Way. And it is, by the standards of supermassive black holes, almost completely inactive. This is deeply strange. When astronomers study active galaxies, objects called Seyfert galaxies, quasars, and blazars, they see supermassive black holes consuming material with extraordinary appetite. The infalling gas heats to millions of degrees as it spirals inward, radiating energy across the entire electromagnetic spectrum. The most energetic of these objects, quasars, can outshine their entire host galaxy by a factor of hundreds or thousands. A single quasar can pour out more energy per second than all 100 billion stars of the Milky Way combined. Sagittarius A star's current luminosity is roughly 10 billion times below what would be expected for a black hole of its mass-consuming material at a typical rate. By almost every measure, it is one of the most underluminous supermassive black holes known. Why? The most widely accepted explanation involves the nature of the gas available for the black hole to consume. Most of the gas near the galactic center is hot, well above warm, well above lukewarm, sitting at temperatures of millions of degrees, heated by the intense radiation environment of the galactic center. Hot gas has pressure, it resists compression, and black holes feed most efficiently on cold, dense gas that falls inward without resisting. Hot gas, even when it is gravitationally bound to the black hole, tends to form a kind of puffed up, diffuse structure around it called a radiatively inefficient accretion flow. In this mode, only a tiny fraction of the gas that enters the black hole's gravitational sphere of influence actually makes it all the way to the event horizon. Most of it is either heated further and driven outward in winds, or it circulates in slow, inefficient eddies that never fully fall in. This is the current best explanation, and it is consistent with observations. But it raises its own question. Why is Sagittarius A star so much quieter even than other black holes thought to be in the same inefficient accretion mode? Some researchers have proposed that Sagittarius A star is simply between meals. The galactic center has had periods of much higher activity in the past, as suggested by the X-ray echoes, the Fermi Bubbles, and the 3 kiloparsec arm. The current quiet phase may be a temporary state, a lull that could end when the next large cloud of gas or the next sufficiently massive object makes it to the center. Others suggest that the black hole's spin rate, the angular momentum it carries, influences how efficiently it can extract energy from infalling material. A slowly spinning black hole may radiate less efficiently than a fast spinner. The quiet of Sagittarius A star is not peaceful. It is a puzzle. In every direction around it, the galactic center is wild and energetic and chaotic. And at the center of all of that, the most massive object in the galaxy sits and murmurs. But even that murmur may be misleading, because what the black hole is not consuming is almost as strange as what it is. And the reason it is not consuming more comes down to a problem with the gas itself. There is gas near Sagittarius A star, a lot of it. Stellar winds from the massive stars orbiting within a few light years of the black hole pour enormous amounts of material into the surrounding space continuously. Estimates suggest that the winds from these stars alone deposit roughly enough gas every year to feed a reasonably active black hole. Sagittarius A star is not a reasonably active black hole. It is consuming only a tiny fraction of what is available. To understand why, you need to understand what accretion actually is. Accretion is the process by which a massive object gathers surrounding material. For a black hole, this means gas spiraling inward, losing energy through collisions and radiation, and eventually crossing the event horizon. But gas does not fall straight into a black hole the way a ball falls straight to the ground. It has angular momentum. It circles, and as it circles closer, it needs to lose that angular momentum somehow to continue falling inward. Inefficient accretion systems, turbulence, magnetic fields, and viscosity within the gas help transfer angular momentum outward, allowing material to spiral inward and eventually fall through. This process is well understood and produces the bright accretion disks seen around actively feeding black holes in other galaxies. At Sagittarius A star, something is disrupting this process at nearly every step. First, the gas entering the black hole's gravitational territory from stellar winds arrives at high temperature and high turbulence. This makes it difficult for the material to settle into a coherent disk structure. Instead of organizing into an efficient accretion flow, the gas forms a hot, diffuse halo that swirls around the black hole without efficiently falling in. Second, even within the hot halo, outflows are taking material away. Observations have shown that most of the gas that enters the gravitational influence of Sagittarius A star eventually gets driven outward again by the pressure of whatever small amount of energy the black hole is producing. The accretion system is essentially leaking. Material comes in, wanders around the black hole's vicinity for a while, and most of it gets pushed back out before crossing the point of no return. The fraction of available gas that actually crosses the event horizon is estimated to be extraordinarily small, perhaps only a few tenths of a percent of what arrives in the black hole's neighborhood. The rest returns to the surrounding environment, heating the gas, driving outflows, and perpetuating the cycle of inefficiency. This is consistent with the radiatively inefficient accretion flow model mentioned in the previous chapter, but it raises a forward-looking question that carries significant implications. What would it take to change this? What would push Sagittarius A star out of its current quiet state and into a genuinely active phase? The answer, based on current models, is a supply of cold, dense gas, something massive enough and cold enough to resist the pressure and turbulence that currently keeps most of the surrounding material at arm's length from the event horizon. There are cold gas clouds in the inner galaxy. Some of them are on orbits that could, over millions of years, bring them close to the galactic center, and there are hints in the observational record that this has happened before. The next time it happens, the entire galactic center will transform, and what that transformation might mean for everything in the Milky Way is something we will face directly before this journey is over. But first, nestled in the quieter pockets of the galactic center, something unexpected is growing. Everything we have discussed so far about the galactic center has emphasized its violence, its radiation, its magnetic intensity, its tidal forces, its chaotic gas flows. This is accurate. The galactic center is an extreme environment by any measure, but embedded within that violence are pockets of startling calm, dense, cold regions of gas and dust that are so thick they absorb nearly all radiation passing through them, blocking light from stars behind them and appearing as dark patches against the bright background of the galactic center. These are called infrared dark clouds, and the fact that they exist near the galactic center at all is another anomaly in a region full of them. In most of the galaxy, molecular clouds, the cold, dense reservoirs of gas from which stars form, exist in relative quiet, far from intense radiation sources. Near the galactic center, the expectation was that any cold gas would be rapidly heated and dispersed by the intense radiation environment, the powerful magnetic field, and the turbulent gas dynamics of the inner galaxy. Cold gas should not survive there long enough to be observationally significant. Several large infrared dark clouds have been identified near the galactic center, some of them quite massive. One of the most studied is called the Brick, a cloud of cold, dense gas located only about 100 light-years from Sagittarius A star. The Brick contains enough mass to form tens of thousands of stars. It is cold by the standards of the galactic center. It is dense, and by every conventional model of star formation, it should be actively forming stars right now. It is not, or at least, if it is, the star formation rate is far below what its mass and density would predict anywhere else in the galaxy. This is known as the star formation suppression problem, and it applies to the galactic center more broadly. The region contains enormous amounts of dense gas that, in a calmer environment, would be forming stars prolifically. Instead, the star formation rate near the galactic center is dramatically lower than models based on gas density would predict. Several explanations have been proposed. The intense magnetic field may be providing support against gravitational collapse, with field lines threading through the cloud and resisting compression. Turbulence in the gas, driven by the chaotic dynamics of the galactic center, may be preventing the slow, steady collapse that star formation requires. High cosmic ray ionization rates near the galactic center may be heating the gas just enough to prevent it from cooling to the temperatures needed for collapse. All of these are active research areas. None has been conclusively confirmed as the primary driver. What the infrared dark clouds reveal is that even within the most extreme environment in the galaxy, matter finds ways to hold itself together, to resist the forces trying to destroy or disperse it. Cold gas near the galactic center is not just surviving, it is waiting, and when conditions finally align, when the turbulence settles and the magnetic support weakens in some local pocket of the cloud, a burst of star formation may follow that is unlike anything seen in the calmer regions of the galaxy. The galactic center alternately suppresses and ignites stellar birth in ways that remain poorly understood, but before any of those stars form, something even more extreme is already there. Objects so dense, so magnetic, so powerful that they represent the far limit of what matter in this universe can become. A teaspoon of neutron star material would weigh roughly 10 million tons on Earth. That gives you a starting point for understanding what a magnetar is. Neutron stars form when a massive star exhausts its nuclear fuel and its core collapses in a supernova explosion. The collapse compresses the core to extraordinary density. In a space no larger than a city, something with more mass than our star is packed so tightly that electrons and protons merge into neutrons, and the resulting object pushes the limits of nuclear physics to maintain its structure. Magnetars are neutron stars with magnetic fields so intense that they dwarf even the already extraordinary fields of ordinary neutron stars. Where a typical neutron star might have a magnetic field roughly 1 trillion times stronger than Earth's, a magnetar's field is 1,000 times stronger still. The magnetic field of a magnetar is powerful enough to distort the quantum structure of empty space itself. At close range, it would disrupt the chemistry of molecules before you could get anywhere near the surface. It would strip electrons from atoms and render any form of matter we understand completely unrecognizable. At a distance of roughly half a mile, the field would be strong enough to fatally disrupt the iron atoms in human blood. There are only about 30 confirmed magnetars in the entire galaxy. Several of them are clustered near the galactic center, within a few hundred light years of Sagittarius A star. This concentration is far beyond what random distribution would predict. This cluster is confirmed by observation. Why it exists is an active area of research. One possibility is simply that the galactic center has produced more massive stars over its history than any other region of the Milky Way. Massive stars are the progenitors of neutron stars, and the most massive among them may preferentially form magnetars rather than ordinary neutron stars. If the galactic center has been a site of intense, repeated star formation events over billions of years, it would naturally accumulate a higher than average population of exotic stellar remnants over time. Another possibility involves the extreme magnetic environment of the galactic center itself. During the supernova collapse that produces a neutron star, the seed magnetic field of the dying star is amplified enormously by the dynamo effect of the rapidly spinning, convecting proto-neutron star. If the progenitor star was embedded in the unusually strong ambient magnetic field of the galactic center, that seed field may have been larger to begin with, resulting in a stronger final magnetar field. This is theoretical. The connection between ambient field strength at birth and final magnetar field has not been fully established. What magnetars near the galactic center add to the overall picture is another layer of extreme physics concentrated in the same region. Magnetic fields strong enough to warp space-time, objects dense enough to crush ordinary matter out of existence, all clustered within a few hundred light years of an already anomalous black hole. The galactic center is not just a place where things are big or fast. It is a place where the physical extremes of the universe converge. Every exotic object and process known to astrophysics seems to be represented there in elevated concentrations. And there may be even more black holes there than anyone expected. Because Sagittarius A star may not be alone, we know about stellar mass black holes, objects between roughly 5 and 100 times the mass of our star, formed when massive stars collapse at the end of their lives. We know about supermassive black holes, the giants at the centers of galaxies, ranging from millions to billions of solar masses. What has remained elusive is the middle ground, intermediate mass black holes, objects in the range of 100 to 100,000 solar masses. These objects should exist in the theoretical framework of how black holes grow over cosmic time. Intermediate mass black holes represent a natural stepping stone between the stellar remnants and the galactic giants. But for decades, clear observational evidence for them proved frustratingly difficult to find. The galactic center may be hiding several of them. Hints have emerged from multiple directions. One line of evidence involves stellar orbits. Certain stars near the galactic center display slight deviations from the perfectly elliptical orbits predicted by the gravity of Sagittarius A star alone. These deviations could be caused by the gravitational influence of additional compact masses in the region. If those masses are not individually visible stars or known compact objects, intermediate mass black holes become a plausible candidate. A second line of evidence involves globular clusters. The Milky Way contains roughly 150 of these ancient, densely packed balls of stars, some of them billions of years old. Theorists have long predicted that the cause of the most massive globular clusters, where stellar densities are extreme and gravitational interactions frequent, should produce intermediate mass black holes through repeated mergers of stellar mass black holes over billions of years. Several globular clusters that orbit the Milky Way pass through the galactic center region, periodically dragged inward by the gravitational pull of Sagittarius A star. As they do, tidal forces from the central black hole strip stars from the outer regions of the cluster, gradually dissolving it. If those clusters contained intermediate mass black holes in their cores, those smaller black holes would be deposited near the galactic center as the cluster dissolves over billions of years of such encounters. This is a theory. It is consistent with the observed properties of several star clusters in the inner galaxy and with simulations of how the galactic center population has evolved, but it has not been confirmed. A particularly intriguing candidate is a compact object associated with a star cluster called IRS-13, located only a fraction of a light year from Sagittarius A star. Several studies have suggested that the gravitational coherence of this cluster, which should have been torn apart by tidal forces at such close range, can only be explained by a central mass far larger than any known star. An intermediate mass black hole of several thousand solar masses has been proposed as the anchor holding the cluster together. This remains contested. Not all analyses agree that an intermediate mass black hole is required. What is clear is that the gravitational environment of the galactic center is complex enough that Sagittarius A star is almost certainly not operating in isolation. The dynamics of the region are influenced by a population of compact objects whose full extent and mass distribution we have not yet mapped. And above all of this complexity, a new pair of eyes has recently opened on the galactic center. What they are seeing is changing everything again. The James Webb Space Telescope launched on December 25, 2021, and began science operations the following year. It is the largest and most powerful space telescope ever built, designed to see the universe in infrared light with sensitivity and resolution that surpasses every instrument that came before it. For the galactic center, this is transformative. Infrared light is exactly what you need to see through the obscuring dust clouds between us and the galactic center. Webb was designed in part for precisely this challenge. Its sensitivity allows it to detect fainter objects than any previous infrared telescope. Its resolution allows it to distinguish individual stars in regions so crowded that previous instruments saw only a blur. And its ability to analyze the infrared spectra of those objects tells us their temperatures, compositions, and velocities with unprecedented precision. The early results from Webb's observations of the galactic center have already revised our picture in significant ways. The number of detectable stars in the inner parsec around Sagittarius A star has increased dramatically. Webb is resolving individual objects in regions that appeared as undifferentiated light to previous telescopes. This expanded catalogue of known objects is allowing researchers to build better models of the stellar population, revisit the missing cusp problem with new data, and search for previously unknown members of the star cluster. The G objects are coming into sharper focus. Webb's infrared imaging has provided cleaner views of the extended envelopes of gas and dust surrounding these peculiar objects, helping researchers constrain the stellar merger model and rule out some alternative explanations. The question of what exactly these things are is no longer completely open. It is narrowing. Infrared dark clouds near the galactic center, including the brick, are being mapped in detail that was not previously possible. Webb is detecting individual protostars within these clouds, the very early stages of stellar ignition that were invisible to previous instruments. This is directly informing the debate about star formation suppression in the galactic center, providing data points that models must now account for. Webb has also begun contributing to the study of Sagittarius A star itself through indirect means. By precisely measuring the positions and velocities of stars in the star cluster with higher accuracy than before, it is refining our knowledge of the mass distribution in the inner parsec, searching for signs of the hypothetical intermediate mass black holes, and testing whether the spacetime around Sagittarius A star matches what general relativity predicts at these scales. Some results suggest very good agreement with Einstein's predictions. Others hint at small discrepancies that could become significant as the data improves. Confirmed deviations from general relativity at the galactic center would represent a revolution in physics. What Webb cannot do is resolve the event horizon of Sagittarius A star directly. That task belongs to the Event Horizon Telescope, the global network of radio dishes that produced the first image of the black hole shadow in 2022. The two programs together, Webb in infrared and the Event Horizon Telescope in radio, are converging on the galactic center from different directions, building a picture more complete than either could achieve alone. This is the most intensively observed region of our galaxy in history, and what we are learning keeps deepening the questions rather than closing them. The picture is growing richer, but the most consequential chapter of the galactic center's story may not be in its past or its present. It may be in its future, and that future is closer than most people realize. Right now, Sagittarius A star is quiet, but the evidence accumulated across this entire journey tells a consistent story. It has been far more active in the past. It is capable of dramatic bursts, even today, and the conditions required to trigger a sustained increase in activity exist within the galactic center. So, what happens if it wakes up? The first thing to understand is scale. An actively feeding supermassive black hole does not produce a local event. It reshapes its galaxy. Quasars, the most extreme examples of active galactic nuclei, flood their host galaxies with radiation intense enough to heat and drive away gas across thousands of light years. The Fermi Bubbles are almost certainly the remnant of a much gentler version of this process from Sagittarius A star's past. A genuinely active phase would be orders of magnitude more powerful. The good news, and it is genuinely good news, is that we are far from the center. 26,000 light-years is a significant buffer. A moderately active Sagittarius A star, producing energy at a fraction of the output of the most powerful known quasars, but still far above its current output, would first affect the inner galaxy most severely. The dense stellar populations near the center would be exposed to dramatically increased radiation and particle winds. Gas that currently sits in cold clouds near the galactic center would be heated, dispersed, and driven outward. Star formation in the inner galaxy could be disrupted for millions of years. Moving outward, the effects diminish with distance. By the time you reach our location in the outer regions of the galactic disk, The radiation from even a substantially more active Sagittarius A star would be attenuated by the intervening gas and dust to a level that would not directly threaten life on Earth. The geometry works in our favor. We are not in the direct line of any jets the black hole might produce, and the galactic plane itself provides shielding. However, indirect effects are harder to rule out completely. A dramatically increased cosmic ray output from the galactic center could, over thousands of years, slowly increase the background radiation environment of the galaxy, including in our neighborhood. The degree to which this matters depends on the intensity and duration of the active phase. The scenario most often discussed in models is not a sudden switch to quasar-level activity. It is a gradual increase, driven by the infall of a cold gas cloud over thousands of years. This slow build would give any sufficiently long-lived civilization enormous warning. The galactic center has no off switch, and equally has no hair trigger. What might trigger the next active phase? The most direct candidate is the Andromeda galaxy itself. Andromeda is approaching the Milky Way. The two galaxies are expected to begin merging in roughly 4.5 billion years. Galaxy mergers are among the most effective triggers of elevated black hole activity known to astronomy. The gravitational disruption of a merger drives enormous quantities of gas toward the galactic centers of both colliding systems. When the Milky Way and Andromeda merge, Sagittarius A star will almost certainly become substantially more active. By then, our star will also have changed dramatically, and Earth, as we know it, will no longer exist. The future of the galactic center is written in physics that we understand. What it tells us about our place in the universe is the final chapter of this journey. We began this journey 26,000 light-years away. Looking inward at a region of our galaxy we could not even see for most of human history, we found a black hole that should not be as quiet as it is, stars that should not exist where they orbit, gas that should not be cold where it sits, structures that should not have the shapes they have, a glow of gamma rays with no confirmed source, threads of radio emission with no clear origin, a population of exotic objects that strain the limits of every category we have built. What does all of this tell us? The most direct answer is that the galactic center is a laboratory, not a human-built one, but the universe's own testing ground for physics under conditions we cannot replicate here on Earth. The densities, magnetic fields, gravitational forces, and particle energies at the galactic center exceed anything accessible to our most powerful particle accelerators by many orders of magnitude. Every observation we make, there is a data point from an experiment we could never design ourselves. And laboratories reveal things. The fact that so much at the galactic center does not match our predictions is not a failure of science. It is science working correctly. Our models were built from observations of the ordinary universe, the vast regions of space where conditions are calm enough for simple rules to dominate. The galactic center is the edge case, the regime where those simple rules break down and the underlying complexity of physics becomes visible. The galactic center is telling us that our models of how galaxies form and evolve are incomplete, how stars form in extreme environments, how black holes grow, how magnetic fields shape the flow of matter at the largest scales, how dark matter interacts with visible matter in high-density regions. All of these questions remain open, and the galactic center is producing the evidence that will eventually answer them. There is a second, quieter message in what we have seen. Every large galaxy we have studied has a structure like ours, a dense center, a supermassive black hole, surrounding populations of stars and gas, shaped by the black hole's influence over billions of years. The galactic center is not exotic in the sense of being rare. It is exotic in the sense of being extreme. What we learn here applies everywhere. The universe is filled with galactic centers. Some of them are active, blazing as quasars visible across billions of light years. Some of them are quiet like ours, sitting in apparent stillness while the physics around them accumulates mysteries. Understanding our own galactic center is understanding all of them, and there is one final thing. You are orbiting this place. Right now, at this moment, our entire solar system is moving through space at roughly 500,000 miles per hour, circling Sagittarius A star in an orbit that takes 230 million years to complete. The last time we were in this position in our orbit, the dinosaurs did not yet exist. In the time it takes you to fall asleep tonight, our solar system will have traveled roughly 360 million miles around the center of the Milky Way. We are not observers of the galactic center from a safe distance. We are participants in it. The black hole at the heart of our galaxy has been shaping everything around it, including the conditions that allowed our star to form, our planet to coalesce, and life to emerge, for longer than the Earth has existed. The math does not always add up at the galactic center. The story it is telling is the story of everything.